Yeah, good evening. I welcome you all to the problem solving session of the NPTEL course on ice engines and gas turbines. Today is week 10 and we'll see some problems on gas turbines and then on the aircraft engines. A regenerative gas turbine with intercooling and reheat operates at steady state. Air enters the compressor at 100 kilopascal 300 Kelvin with a mass flow rate of 5.807 kg per second. Uh, can you confirm if I'm audible? The pressure ratio across the two-stage compressor as well as the turbine is 10. The intercooler and reheater each operates at 300 kilopascal, and at the inlet, at the inlets to the turbine, stages, the temperature is 1400 Kelvin. The temperature at the inlet to the second compressor stage is 300 Kelvin. The efficiency of each compressor and turbine stage is 80%. The regenerative effectiveness is 80%. Determine the thermal efficiency, the back work ratio WC by WT, the net power developed. So we are given um, a gas turbine which has regeneration and intercooling reheating. So it has all three. First we would draw the schematic. So there is it has two-stage compressor and two-stage turbine. So first stage, starting with the first stage compressor. So it compresses to a second state. This is a state 1, this is state 2, and there is a intercooler, and there is a state 3, and then there is a second compressor C2, and there is a reheating. There is a regeneration. So we would draw it like this, and then there is a combustion chamber. Can be this is combustion chamber. This is a heat exchanger for regeneration, and then there's two-stage turbines, and there is a reheating in between. So first stage we have a T1 which expands, and then there is a reheating, and then there is a second stage turbine, and from the outlet of this is taken to the heat exchanger for the regeneration like this. So now we had state 3, this is 4, this is 5, 6, 7, 8, and 9, and 10. So here the air enters at 100 kilopascal and 300 Kelvin. So P1 is 100 kilopascal and T1 is 300 Kelvin. And it is also said that the air enters at the second stage of compressor also at 300 Kelvin. So this is also equal to T3. And the temperature, the intercooler and reheater each operates at 300 kilopascal. So that means P2 is equal to P3 is equal to Preheater is P7 equal to P8. All these are 300 kilopascal, and both the turbine inlet temperature is 1400 Kelvin. So that means P6 and P8. Sorry, T6 and T8 were 1400 Kelvin. Efficiency of all the compressor and turbines are C1 equal to efficiency C2 equal to efficiency T1 equal to efficiency T2 equal to 0.8. The effectiveness is also 0.8. So P2 is the 300 kilopascal, P1 is 100 kilopascal. So we know that the pressure ratio across this is 3, and then based on this we can calculate the work done by the C1. So first we need to calculate T2. T2 by T1 is T2 by P1 power gamma minus 1 by gamma. So T2 is T1 into P pressure ratio, or P2 by P1 power gamma minus 1 by gamma. So T1 here is 300 Kelvin, and P2 is 300 kilopascal, and P1 is 100 kilopascal. And power, this is 0.4 by 1 by 4. Can you calculate the value of T2? Hello, sorry, did you tell the answer? I couldn't hear you.
Yes, sir. Yes, sir. I'm
Calculating?
calculating, sir.
Okay, fine.
Yes, sir. Sir, 410 Kelvin.
410
410,
point
410.6 Kelvin.
6
6.
Kelvin. Okay. Now, how can we calculate the compressor work?
T2 minus T1, sir. WC CP into T2 minus T1.
Cp into T2 minus T1. So basically it is the change in enthalpy, H2 minus H1, and that we can approximate it to, if you are assuming ideal gas properties, then Cp is constant for at all the temperatures. So we are approximating this. So this is 1.005, T2 is 410.62 minus 300. Can you calculate C1? Please.
111.17, sir.
111.17. Yeah.
Sir.
What is the unit?
Watts.
Watts? No. This is work done, no? So Cp will take a unit of Cp will take kilojoule per kilogram Kelvin, and then we have multiplied with some Kelvin. So we will finally end up with kilojoule per kilogram. What it means is, if we have put 1 kilogram of air, what is the kilojoule that we have to spend for the compressor? So that is kilojoule per kilogram. Similarly, For W, we need to calculate T3 and T4. T3 is known, that is again 300 Kelvin. T4 we have to calculate. So T3 by T4 by T3 is again P4 by P3 power gamma minus 1 by gamma. So T4 is equal to T3 is 300 and P4 at the end of they say the pressure ratio across the two-stage compressor and turbine is 10. So that means P4 by P1 is equal to 10. So P4 is equal to 10 times of P1 and that would be 1000 kilopascal. So here P4 is 1000 kilopascal and P3 is 300 kilopascal. Now we have 0.4 by 1.4. And calculate T4.
423.17.
423.17 Kelvin. And again for the second compressor's work, we will have Cp into T2 minus T1, that is Cp into T4 minus T3, and that is 1.005 into 423.17 minus 300.
$123.78.
123.78 kilojoule per kilogram. Now similarly we can calculate turbine work, both the turbine work.
Yes, sir.
So T6 is known. No, I think yeah, T6 is known. That is 1400 Kelvin, and P6 and P7 are known. P6 pressure at 6 is known. That will be same as pressure at 4, right? So that is 1000 kilopascal. So P6 is equal to 1000 kilopascal, and at the end of turbine 2 is P7, and that we have they have told reheater, and at the reheater it is 300 kilopascal. So P6 P7 is 300 kilopascal. So W turbine 1 is equal, we need to find the temperatures. T6 is 1400 Kelvin, T7 is unknown. So we have T6 by T7 equal to P6 by P7 power gamma minus 1 by gamma. So T7 is equal to T6 divided by P6 by P7 whole power gamma minus 1 by gamma. So T6 is 1400 and P6 is 1000 by 300 whole power 0.4 by 1.4. Calculate T7.
$992.5, sir.
992.5 Kelvin. So turbine work is Cp into T6 minus T7. So 1.005. T6 is 1400 Kelvin minus 992.5. It is turbine work.
Sir, 409.5 kilojoules per
Kilojoule per kilogram. Now similarly we can calculate the second turbine. For second turbine we
Sir, once, yes, sir.
Yeah.
One second, can you show the last slide, sir? Last slide.
Yes.
Yes, sir. Thank you.
Okay. So second turbine we have 8 and 9. T2 we have, this is 8 and this is 9. At state 8 we know temperature is 1400 Kelvin and this pressure is 300 kilopascal and this is 100 kilopascal, and but T9 is not known, so we can calculate it. T8 by T9 is equal to P8 by P9 power gamma minus 1 by gamma. So T9 is equal to T8 divided by P8 by P9 gamma minus 1 by gamma. T8 is 1400. This is 300 by 100 power 0.45. Can you calculate T9?
1022.8, sir.
0.8 kilojoule per kilogram. So for compressors we had
So which book I have to follow for this question, for these types of questions?
there is some Saravanan Sahu, something like that. PK will have some questions like this. Let me check. It was not given in the uh, suggested book list. I don't remember the exact name. It is something like Saravana Muthu Sahu, something like that.
Okay.
Saravana Muthu. Can you see?
Okay, sir.
Yeah.
Yes, sir. Yes. I was following PK Nag book, sir, and other
PK.
books.
Yeah. I think this problem is exactly taken from that Saravana Muthu. So next is for turbine 2, this is Cp into T8 minus T9, that is 1.005, 1400 minus 1022.8, and calculate this.
379.
379 kilojoule per kilogram. Now Wc is equal to Wc1 plus Wc2. C1 is 111.17, 111.17 plus 123.78. Can you calculate compressor work?
234, 235, sir.
235. Okay. Similarly, turbine is WT1 plus WT2. That is 409.5 plus 370.
788.
788 kilojoule per kilogram. So we had to calculate back work ratio. WC by WT, that is 235 by 788.
0.29.
0.29. But they have given 0.454. I think we didn't consider the efficiency, right? So if we consider the efficiency, so efficiency will be like actual work by theoretical work is the efficiency, right? So whatever we have calculated earlier is for the isentropic case. Now for actual case, we will have say WC1 actual, or right, efficiency C1 is equal to compressor work. In actual we will have more work, right? So this is actual redact easy by theoreticals. Now that means WC1 actual is equal to WC1 theoretical, that is 111.17 divided by 0.8. That is
138.
138.
Okay.
So based on this, we have to also calculate the actual outlet temperature. So far we have calculated the theoretical outlet, so actual can be found out. Similarly for C2 is 123.7 divided by 0.8.
155.
155 kilojoule per WT1 actual is 400. So this is 409.5 into 0.8. Sorry?
327.6.
327.6 kilogram. WT2
303.2.
Now WC is equal to actual 138 plus 155.
293.
Actually is 327.6 plus 303.
630.8.
I think this will reduce the ratio, right? It is 300 by 5. So now backward relation. Two 93 by 293 divided by 630.
0.46.
0.46.
Yes.
We are close. Now, to calculate the efficiency, we need to know the change in the this how much heat exchange heat is given from 4 to 5 and how much is given from the combustion chamber, and also in the reheating 7 to 8. For this we need to we need to know the outlet temperature of, say, compressor C2, say T4. Currently we have calculated the isentropic outlet temperature, but in actual it will be little more. So that has to be found, and similarly T7 has to be found, and then using effectiveness we can calculate the fifth point temperature. And net power developed, I think we can already do it. Mass flow rate with a mass flow rate of 5.07 kg per second. So here W net is W turbine actual minus W compressor actual, that is 630.8 minus 293.
337.8.
337.8 kilojoule per kilogram. And now W dot net is equal to M dot into W net. M dot is 5.807 into 337.8.
1961.
1961.
0.6.
This is kilojoule per second. So this is 1960, say 2 kilowatt. But they have given 2000 some kilowatt. 2046. Okay, we can find this temperatures T4. Beta C2 is equal to 0.8, so that means W C2 theoretical divided by W C2 actual, and that is T inlet outlet is T4. T4 isentropic minus T3 by actual T4 minus T3. So this is 0.8 is equal to, and T4 minus T3 is what we have already calculated. T4 is 423.17. 423.17 minus 300 by T4 minus 300. So T4 is, so whatever we have calculated here is theoretical. So I would write TS here is okay. Now T4 is 300 plus 423.17 minus 300 divided by 0.8.
453.93.
453.93 Kelvin. So T4 is known. Similarly, T7 and T8 is needed. How do we calculate T7? Eta T1, sorry?
Turbine work peak. Using turbine work we can find out.
So eta turbine work is turbine 1 actual by WT1 theoretical. So in actual it will be that CP into, we will have T, what is the inlet of turbine 1? 6 to 7. So we will have T6 minus T7 by Cp into T6 minus T7 isentropic. T6 is 1400 Kelvin minus T7 is not known, and here we have 1400 minus T7 is we have already calculated. T7 is here 992.5. So this is 992.5. So now this is 0.8 on the efficiency is 0.8. So T7 is equal to 1400 minus 0.8 of 1400 minus 992.5.
1074.
1074 Kelvin. Similarly, if you write expression for,
one second, sir.
yeah.
Yes, sir. Okay.
So this we will have WT2 actual divided by WT2 theoretical, and this is T2 is between 8 and 9. So this is T8 minus T9 by T8 minus T9 isentropic, and this is eta T2. So we have 0.8 is equal to T8 is 1400 minus T9 is 9s is 1022.8, and this is T9. So T9 is 1400 minus 0.8 times of 1400 minus 1022.8.
1098.24.
1098.24 Kelvin. So T9 is known, and the effectiveness, how do you define effectiveness?
Effectiveness.
Effectiveness of heat exchanger is actual heat transfer by maximum possible heat transfer. Okay. So actual heat transfer is we can take on the high temperature side. So actual heat transfer is can be given by enthalpy change between the 9 and 8, 9th and 10th state. So it will be T9 minus T10. But but maximum heat transfer is when the 10th state is cooled down to the inlet of the cooled phase. So that is T4. So when this stream when this stream comes to the temperature of T4, then that is the maximum possible heat transfer. It cannot transfer further, right? So that is maximum state, and then we can write this as actual heat transfer is T9 minus T10, and maximum is T9 minus when the T10 has become T4. So this is T4.
Okay.
So this is effectiveness. So here we know T9 value. T4 is also known, right? Only T10 is unknown, so we can calculate T10. Effectiveness equal to 0.8 is equal to T9 minus T10 by T9 minus T4. This is T9 is 1098.24 minus T10 is the only unknown. This is 1098.24 minus T4. T4 is 453.93. 453.93. Now T10 is equal to 1098.24 minus 0.8 times 1098.24 minus 453.93. Can you calculate T10?
582.79. 582.79.
82.79 Kelvin. So this is T10. Now we know what is the heat transfer between the heat exchanger. So heat transfer in this in the hot stream should be same as the heat transfer in this hot stream should be same as the heat transfer in the cold stream.
That is going to be the maximum heat, right?
No, maximum heat transfer is that when T10 goes to T4. So now that effectiveness we have used to solve to find the value of T10. That is done.
Yes, sir.
Okay. Now we need to calculate what is the heat that is transferred across this, so that we can calculate the fifth state. Okay. Why we want fifth state is next we need to calculate the thermal efficiency. So thermal efficiency is the heat given by the combustion chamber. So we know the outlet temperature of combustion chamber T6, that is 1400 Kelvin, but we don't know the inlet temperature of combustion chamber. So that is the enthalpy given in the combustion chamber, or the heat energy given in the combustion chamber, right? So for that we need T5, and T5 is the if we know that T4 is already known, we have calculated. If you know the heat that is transferred through the heat exchanger, we can calculate T5. So that is on the hot stream it is from 9 to 10. So the same enthalpy change will occur on the cold stream 4 to 5.
Yes, sir.
Okay. So heat transfer is equal to, you can write this as enthalpy 9 minus enthalpy 10. This should be same as enthalpy 5 to 4, right? Or 5 to 4. Yeah. Enthalpy 5 minus enthalpy 4. And this can be, if you put Cp and all everything common, then this is T9 minus T10 is equal to T5 minus T4. T9 is
1098.2.
9.24. T10 is 582.79, and T5 is T4 is
T4 is 453.
453.93. Yes. 453.93. So T5 is equal to 1098.24 minus 582.79 plus 453.93.
969.37.
939.37 Kelvin. So this is T5. And so now Q added in heat exchanger combustion chamber is Cp into T7 minus T6. Sorry, T6 minus T5. T6 minus T5. T6 is known, that is 1400 Kelvin, minus T5 is, we have calculated 969.37. 969.37.
Four 32.79.
432.59 kilojoule per kiloton. So this is the heat we have added in the combustion chamber, right? 432 kilojoules. And what is the work output we have got?
Some combustion.
So we have got 337.8, right? So can we say efficiency is 432.59 and the work output is 337? Can you say this? So this is around, sorry?
Yes, sir, 78.
So this is 78% efficient, gas turbine efficiency, right? So we mean to say if you give 100 joules of heat energy, we will get 78 joules of work output.
Yes, sir.
Is that possible?
No, actually.
So we say Carnot efficiency, right? Carnot efficiency is the maximum efficiency that we can get. So that is TL by TH, right? So approximately we can say TL is, low temperature is 300 Kelvin and high temperature it goes up to 1400, right? We cannot directly say this because it doesn't stay at 1400 for the during the entire heat addition, correct? No. So Carnot efficiency TL, here it will be like this, but in our cycle it will not, it will be something like constant volume heat addition, it will be like this, no? So this point is 1400 Kelvin. So here this is entirely 1400. So both are different. Anyway, just for analysis, if we take this as a efficiency, Carnot efficiency is also around 78, right?
Yes, sir.
In actual, this turbine efficiency will be much lesser because we have a cycle like this. If you take an average heat added thing, it will be not 1400, right? So it will be somewhat say 1000 or something. Anyway, so this 78% is too high. So can you say where we have gone wrong? So we have a compressor one where we compress the air to some 300 kilopascal, and then we have an intercooler where we take some heat out of the stream, and then we again T3 is again 300 Kelvin back to the same original temperature, and then we further compress to 1000 Pascal, and then we have a heat addition through a regeneration, and then we have combustion chamber where we give fuel to heat, and then we have a turbine one where we, from the high temperature high pressure gas, we extract some work output, and then we have a reheater where we again add some heat to the system, and then we have a second turbine, and then it goes out. Yeah. So is this a combustion chamber is the only place where we give fuel input, fuel heat input, or is there some other place where we give?
Combustion chamber is.
Yeah, combustion chamber is one.
Yes, sir.
Yeah. Is there any other place where we give?
where we are giving heat.
Yeah,
Yeah, yes, sir. Reheater also.
yeah, reheater we are giving some heat, right? So that heat also should
Mm.
come from fuel. So that
Mm.
also we should consider, right?
Mm.
Whereas in intercooler, we are taking the heat output. So you just cool down to ambient using some perfect heat exchanger, that is possible. And regeneration also, we saw that from the temperature, ninth temperature, we come down, cool down to 10th temperature by heating the stream from 4 to 5. But
Mm.
reheater 7 to 8, we are only adding fuel. We do not have any other source within the system. So we are giving fuel input. So that temperature should be, that heat input should be added. So in addition to the QCC, we will have Q reheater. So that is Cp into T8 minus T7. T8 is 1400 Kelvin. T7 is 1074.
327.63.
327.63 kilojoule per kilogram. Now total heat input is QCC plus Q reheater. QCC is 432.59 plus 327.63.
760.22.
760.22. So now efficiency is network output divided by Q total. That is Q net is, sorry,
Now it is
W net.
44. I
Yeah,
mean, uh, yes, sir. 0.44.
45%. Okay. W net is 337.8, 760.22. That is 44%. I think that is given in the problem, 44.3. Somehow the work output alone we were not correct. You are studying undergraduate or
Yes, sir. I'm doing BTech in mechanical engineering.
okay? Where? Which university?
Hindustan Institute of Technology, Chennai, sir.
Chennai. Okay. I am also from Chennai. I
Okay, sir.
am doing PhD in IT Madras.
IT Madras.
Yes, yes. For you, the this is part of your coursework or?
No, sir. This is my interest. Like
Oh, okay, okay.
that.
Which year you are in?
I'm in third year now.
Third year. Okay, okay. So
So one
next you
second.
want
Last,
to? Sorry.
I will take screen. Last slide.
Yeah. Anyway, I think I will
Okay.
send. I will send all this in PDF. You are able to see, right?
Okay, sir.
This will be uploaded in the Google Drive, and the Drive link will be shared in the portal.
Okay.
So, for example, oh, this is so. So you can see this screen, right?
Mm. Yes, sir.
Yeah. So if you go to this problem after books and text script and all, you have problem solving session. Recording you can
Mm.
go and then click on this. You will get just. Google Sheet like this. So for every week, different TAs are there, no? So this are YouTube link, and then we have presentation folder. So for me, if you go,
this is also posted in the YouTube also, sir.
yeah,
This
video
recording.
recording is also there in YouTube. All previous videos also you can see, and for other TAs
Okay.
also you can see. So then this Google Drive link till 9th week I have uploaded.
Okay, sir.
So next problem, in a regenerative gas turbine power plant, air enters the compressor at 1 bar 27 degrees Celsius and is compressed to 4 bar. The isentropic efficiency of the compressor is 80% and the regenerator effectiveness is 90%. All of the power developed by the high pressure turbine is used to drive the compressor, and the low pressure turbine provides the net power output. So it is a regenerative plant. The compressor from 1 to 4 bar. So and then there is a regenerator. So there is a high pressure turbine and a low pressure turbine. High pressure turbine directly drives this one, and low pressure turbine provides a net output of 97 kilowatt. Each turbine has an isentropic efficiency of 87%, and the temperature at the inlet of high pressure turbine is 1200 Kelvin. Determine the mass flow rate of air to the compressor, thermal efficiency, the temperature of air at the exit of regenerator. So seems like there is only one stage of compressor and two stage of turbine. And compressor effective isentropic efficiency of compressor is given, and turbine is also given 87%. So we have seen each compressors here, and then there is a regenerator, and then there is a compression chamber, and then turbine 1, and then there is turbine 2. From here it goes back. This is 1, 2, 3, 4, 6, 7. T1 is 27 degrees Celsius is 300 Kelvin. P1 is 1 bar. P2 is 4 bar. Effectiveness of efficiency of the compressor is 0.8. Effectiveness of the regenerator is 0.9. Eta T1 is equal to eta T2 is equal to 0.87, and compressor equal to W dot of turbine 1 is equal to 97 kilowatt. Oh no, sorry. These two are equal, but the other one, W dot T2 is equal to 97 kilowatt. All the power developed by the high pressure turbine is used to drive the compressor, and the low pressure turbine provides net output. Each turbine has an isentropic efficiency is given, and inlet to the high pressure turbine, that is T4, is 1200 Kelvin. So how do we start? We know from 1 to 2, that is T2 can be calculated using pressure ratio, and then that would be isentropic exit temperature, and then we can calculate the actual temperature. With this we can calculate the work of the compressor. So with this work we know what is the work output of the turbine 1. Then we know the work output of turbine 1, and T4 is also known. Then we know what should be the value of T5. So based on that we will get the we'll fix the T5 pressure and temperature, and we can calculate T6 and other states and so on. Okay, so for the compressor, T2 by T1 is equal to T2 by P1 power gamma minus 1 by gamma. So T2s is equal to T1 is 300 Kelvin into 4 power 0.4 by
445.8 kelvins.
8 Kelvin. Okay, this is second this one, and efficiency of the compressor is 0.8, right? Yeah, 0.8. So that is actual work done by the work done to the compressor will be more, so that will come in the denominator theoretical. So this is between 1 and 2, right? So this is T2 minus T1, T2s minus T1, and T2 minus T1, that will be 0.8. Now 0.8 is equal to T2s is 445.8 minus T1 is 300 divided by T2 minus 300. T2 is equal to 300 plus 445.8 minus 300 divided by 0.8. And calculate T2.
Okay. That's 300. 482.25.
482.25 Kelvin. Now WC is equal to Cp into T2 minus T1. That is 1.005. 482.25 minus 300.
183.16.
183.116 kilojoule per. This is same as turbine 1. So turbine 1 worked from turbine 1 is Cp into T5 minus T4, T4 minus T5, T4 minus T5. That is 183.16 equal to 1.005. T4 is 1400, sorry, 1200, right? T4 is 1200 minus T5 is what we need to calculate. No, I think it is 1200 minus this.
One 1017.75.
1017.75 kilojoule, sorry, Kelvin. So we have got T5. So we can calculate P5. So to calculate that, we need to know the isentropic T5. T5 if it had been isentropic process. So we can make use of the turbine efficiency. It is WT1 actual by WT1 theoretical. That is T4 minus T5 divided by T4 minus T5s. This is 0.87. T4 is 1200 Kelvin minus T5 is 1017.75 divided by 1200 minus T5s. So T5s will be 1200 minus 1200 1017.75 divided by 0.87.
So 990.51.
990.51 Kelvin. Now we can calculate the pressure. T4 by T5 is equal to T4 by T5 power gamma minus 1 gamma. CBS. So here we have 1200 divided by T5s is 990.51. P4 and P5. P4 is known because the end of compressor is 4 bar, so that means P3, P4 everything is 4 bar, and P5 is only unknown. This is 4 bar by P5, this is 0.4 by 0.4. So we have 4 by P5 is equal to 1200 by 90.51 power 1.4 by 0.4. P5 will be 4 divided by 1200 divided by 90.51 power 1.4 by 0.4.
2.043.
P5 is 2.
2.043.
Okay. This much bar.
Yes, sir.
Now we have calculated P5, right? So okay. P5. So we know T5 also. Okay. So we know T5, P5, then T5 by T6. It is a second stage compressor. Actually, if there are two compressors, there should be a reheating in between. Or I think it is just two kind of turbines. They didn't talk about reheating. So just two different turbines, high pressure and low pressure turbines. So now P5 is known, P6 should be 1 bar, and P5 to P6. So T5, this is 2.043 by 1 power 0.4 by 1.4. T5 is 990.51 divided by T6. So T6 is 990.51 divided by 2.043 power 0.4 by 1.4.
807.62.
807.62, and this is isentropic. Now in actual, WT2 beta T2 into WT2 actual by WT2 theoretical. So this is 0.87, and WT2 actual is T2 actual is between 5 and 6. No? So T5 minus T6 divided by T5 minus T6 isentropic. This is 0.87. T5 is 990.51 minus T6 is 990.51 minus this is 807.62. T6 is 990.51 minus 0.87 of 990.51 minus 807.62.
Sir, 831.43.
Kelvin. Okay, so now WT2 is equal to Cp into T5 minus T6, that is 1.005 of 990.51 minus 831.4.
159.86.
159.86 kilojoule per kilogram. And we were told that power output of the low pressure turbine is T2, sorry, WT2 is 159.86 kilojoule per kilogram. W2 rate is 97 kilowatt. It's 97 kilowatt. So W2 is equal to m dot into WT2. And this is 97 is equal to m dot into 159.86. So m dot is equal to 97 divided by 159.86.
Point
0.60 kilogram per second. I'm getting the same. They have got 0.562. We lose some efficiency somewhere. Did you round off or it is completely 0.6? Anyway, we can proceed. So, what is the next one? We need to find the outlet temperature of this T7, temperature of the air at the exit of the regenerator. So, do we know temperature at T3? No, T2 is known, right? T2, yeah, T2 is known. T6 is what we have just calculated. For regenerator, I will just close. Effectiveness is point. Point 9. That is actual heat transfer by maximum heat transfer. So actual heat transfer is T6 minus T7, T6 minus T7, and maximum is T when T7 has become T2. So this is 0.9. T6 value is T6 is calculated. T6 is 831.4. 831.4. T2 is should be more. T2 482.4. So this is T7. T7 is can you calculate T7?
Sir, 517.165.
517.6. They have got 523. It's okay. Now we can calculate T3. So in the heat exchanger, the heat transfer to both the stream would be the same. So that means H6 minus H7 is same as H3 minus H2. It is T6 minus T7 is T3 minus T2. T6 is 831.4 minus 517.16. T3 is the unknown. T2 is 482.25. So T3 is equal to 831.
796.
Sorry, 7?
796.5.
796.5 Kelvin. T3 is known. Now heat transfer heat given is QCC is equal to Cp into T4 minus T3. T4 minus T3. T4 is 1200 minus T3 is 796.5.
405.52.
Sorry,
405.52.
405 kilojoule per kilogram, and net work output would be the work output of turbine 2. So that is 159.86. So efficiency is 159.86 divided by 405.52.
0.39. 0.3.
So 39%. They have got 43%. 43%. Can you find anything, or
W2 actually. So what is the value of W2 work of turbine actually?
this is not WT2 159.86?
And thermal theoretical.
Theoretical, I think we didn't calculate. We just had a T6 isentropic 807.62, and we found T6 actual is 831.4. You mean to say maybe they would have taken the theoretical turbine output? Then it would be 87%, right? So it will be 0.39 by 0.87. It is 44.8. They got 44.3. Oh, sorry, 43. Maybe. I think we can move on to explore. Determination of the specific thrust and SFC specific fuel consumption for a simple turbojet engine having the following component performance at the design point at which the cruise speed and altitude are Mach 0.8 and 10,000 meters. Compressor pressure ratio is 8.0, turbine inlet temperature is 1200 Kelvin, isentropic efficiency of compressor is 87, turbine is 90, intake is 93, propelling nozzle efficiency is 95, Mechanical transmission efficiency is 99. The combustion efficiency is 98. Combustion pressure loss is 4% of the compressor delivery pressure. So the altitude is given as 10,000 meters. So if we have a table, yeah,
this is gas table.
this is ideal gas properties of atmosphere at high altitude.
I think I have sorry.
Okay. So from this we will need temperature, pressure, and speed of sound. So at 10,000 meters, temperature is minus 49.5, pressure is 26.5. Temperature T is equal to minus 49.9 degrees Celsius. Pressure is 26.5 kilopascal, and sonic speed of sound is
3 point.
Sorry, 299.5. 299.5 meter per second. And this to convert in Kelvin.
223.15 kelvins.
Okay, 223.15 Kelvin. Okay, now can we calculate the now if we calculate the stagnant at Mach number 1, if you want to calculate the stagnation temperature,
Yeah.
then this will be TA plus CA square divided by 2CP. It is 223.1. Actually, this is C is actual velocity. So plus.
Velocity.
So we are the flight is going at Mach number 0.8. So then this is 0.8 into 299.5 the whole square divided by 2 into 1000.
28784.
28784.
1 second, sir. 1 second. Yes, sir, it's coming huge. Sorry, one mistake I did. Sir, 251.6.
251.6 Kelvin. So do you know how this turbojet engine will look like? We have different components like compressor, turbine, intake, propellant nozzle, and all.
Yes, sir, I have some idea about it. Last lecture, I have Week 9, sir has explained about it.
Hmm. You remember?
Yes, sir?
Do you remember?
Yes, sir, yes, I remember.
Yeah. So first, what would be the component from your unit?
Compressor.
Compressor?
Yes, sir. The air will come inlet is air will come into the engine,
Hmm.
thereby
So,
compressing the air.
so first before compressor, what is the component?
Fan.
No, we have intake.
Oh, yes, sir.
Intake
For
is like
intake.
a diffuser that will
Mm.
increase the pressure.
Mm.
So that we represent by this. Yeah. Then we have compressor. So this is intake. Then we have compressor. Okay. And then we have what is the next component? We have combustion chamber and then given to a turbine and then it is given to a nozzle. Nozzle will be here there is a mechanically the turbine and mechanically the compressor and turbine are connected. So we do not take any work output from the turbine. We are only interested in having the high exhaust gas flow. So we have found the stagnation temperature. Similarly, stagnation pressure will be the temperature is 1 plus efficiency of the intake CA square 2 by 2 CPT. This is 1 plus intake efficiency is 0.93. This is 0.8 into 299.5 so whole square divided by 2 into 1005 into TA is 223. Can you calculate this?
Mm. 1.48. I'm getting, sir. 1.48.
Yeah, 1.482. This is a pressure ratio. So now P01 is 1.482 into 26.5 kilopascal.
39.28, sir.
39.28 kilopascal.
So these formulas have not been taught in the class, sir. Is it important to study for the exam? These things?
This thing didn't come like intake. The efficiency of the intake it was not taught.
Yes, sir. That was taught, sir. But this formula I'm seeing for the first time, no?
Maybe it was in a different form, like intake of the say the efficiency of the intake is given as the actual temperature difference by theoretical temperature, something like that. No?
Okay.
Okay, you
Okay,
can
sir.
check if it is there. Then this writing the formula in a different version for finding the pressure ratio. But if it is not there, you can leave it. So this problem is from the Krishna Muthu book. But pressure ratio you would have seen, no? Except for this, you would have seen, right?
Yes, sir.
Yeah, only this is.
This is applying in the college, sir. Like gas dynamics subject.
Ah, oh, but not in this course.
Yes, sir.
Oh, okay. Anyway, we'll just. So then, at outlet of compressor, P02 is equal to pressure ratio into P01, that is 8 into 39.2 kilopascal. Can you calculate P02?
314.24.
314.24 kilopascal. Next is to find the change in the enthalpy in the compressor. We have T01 by efficiency of the compressor, then P02 by P01. So P02 is, so this is P02 by P01 is 8. 8 power 0.4 by 1.4 minus 1. And this is 251.6 by 0.87.
234.66.
34.6 Kelvin, and T02 will be T01 plus 234 point, it is 250.19. T01 is 251.6 plus 34.
486.2.
456. Okay. Now work in the compressor is Cp into T02 minus T01, that is 1.005 into 486.2 minus T01 is 251.6.
235.8. 235.8.
Next, with mechanical efficiency,
99.
yeah, so that is compressor work by turbine work, and
0.99.
yeah, WC is 235.8 by 5, it will be almost the same.
238.18.
238. Now turbine work can be CPG into T03 minus T04. T03 is no. So it's given us 1200 somewhere. Turbine inlet temperature is
I mean,
3.
comparison.
So now we need to know CPG. So CPG can be used by gamma as 1.33 at high temperature. So but RA of gas is 287 joule per
Gamma
kilo.
or by gamma minus
So how do we calculate this? We know RA is equal to Cp minus Cv, and Cp by Cv is equal to 31.33. Cp is equal to gamma into Cv, so Ra is equal to Cp of gamma minus 1. So Cpg is equal to Ra divided by gamma g minus 1. That is 287 divided by gamma
869.69.
869. No, I think I know something.
So gamma or by gamma minus 1.
What is gamma by gamma minus 1?
To find out the Cp value,
Gamma R, gamma G by gamma minus 1 into RA. That is 1.33 by 0.333 into 287.
1159.3.
Joule per kg Kelvin. So now turbine work is 1159 into T03 is 1200 minus T04, and T turbine is also known, that is 238.18 equal to this will become 1.159 into 1200 by T04.
994.5.
990. Okay, now P03 equal to P02 into 1 minus PB by P02. So this is a pressure combustion pressure loss delta P. So this is P02 is calculated. Yeah, it's P02 314.24 1 minus 0.04
301.6.
kilopascal. Here whatever we calculated is isentropic. So if you use the temperature turbine efficiency, we will have T04 minus T03. This is actual by T04 minus T03.
Turbine itu turbine hotel itu itu
Efficiency, turbine efficiency is 90%, right? Turbine efficiency is 90%. So 0.9 is equal to T03 1200 minus T04 is T04 is 1985 divided by 1200 minus 994. So T04 is equal to 1200 minus 0.9 into 1200 minus 994.
2015.
It seems like T04 equal to T03, T04, T03.
$153.59.
So nozzle pressure ratio is P04 by P ambient. P04 is 153.59, but ambient is 26.5 grams. So this is
5.8.
5.8 is a pressure ratio, right? But we can find the critical pressure ratio. It is P04 by P critical is 1 by 1 minus the efficiency gamma minus 1 by gamma plus 1 power gamma by gamma. Can you calculate this?
Answer 1.
1.
Yes, sir.
See, this is 1 by 1 minus 1 by 0.95. Can calculate the other term about 0.33 by 2.33.
0.33 divided by
2.33
2.33.
divided power 1.33 by 0.33.
So, 1.33 divided by 0.33. 3.79 10 to the power of minus 4. She could reduce it.
No, I think this power is for the whole thing. It is like this. Sorry. Then we will have 1 minus 1 by 1.33 by 2.33. And here we have 1.33 by 0.33.
916. 916.
1.916. So this is a critical pressure ratio, but our actual nozzle pressure ratio has become more than that. So that means we are in a choked flow condition. So T5 equal to Tc into Tc, and it is 2 by gamma plus 1 power T0. It is 2 by 2.33 into, and it is T0 1015 101.
871.24.
871.24. And P5 is equal to PC equal to P04. That is 1 point. What is P04? 153.5. 153.5 divided by the choke flow condition pressure is 1.916.
80.34. 80.34.
Okay, so rho phi is PC by RTC. So if you calculate, it will be 0.275 kilogram per meter cube. So C5 is gamma RTC. So that will be here running out of time, so I'm just writing the values. 5 per second. So this is jet velocity. Now A by m, we have m dot is equal to rho phi A C5. So if you calculate A by m, it will be 0.00637. So specific thrust Fs, F by m That is E5 minus E. So specific fuel consumption is the fuel flow rate. So this will be in kilogram per second and divided by specific the trust we have found specific trust. So this is 0.01843600 divided by 80.7. So 1 kg per hour per minute. Anyway, I think this is not much needed. I just wanted to introduce some different programs. You have any questions?
No, sir. I have to revise the topic.
Yeah. Okay. Thank you.
Thank you, sir.
We'll see you in the next session.